Hi everyone, so this is the last installment in our Transformers lecture series, and we are going to look at this time three-phase transformer configuration. So we're zooming out a little bit from our circuit diagram, our equivalent circuit view of the transformer, and we're going to look at how these transformers are connected together from single phase to three-phase arrangements. So by the end of the session, you should be able to draw connection diagrams for delta and Y connected transformers, and you should also be able to calculate voltages and currents in three-phase transformer configurations. Here we are not talking about equivalent circuits and calculating the voltage drops and so on across them. I'm just talking about tracking the voltages from delta to star to delta, etc. across the transformer. So we are taking a more of a bird's eye view of the problem. So one of the things that is important to remember here is that when the systems are balanced, since the phases are identical, a three-phase system can be analyzed as three single-phase systems. So we only really need to look at one phase. So the same equivalent circuit we have seen before, our transformer is really just three of these and connected in different ways. So we'll focus now, since we are not going to bother with the losses for this part. It's not that the losses are not there. You could still get questions with the losses in them, but since you'd be able to treat those individually, you could reduce the three-phase system problem to just a single-phase system problem by figuring out what is the line voltage, what is the phase voltage, etc., and using that in your single-phase circuit. And then you would be able to you do the question as you would have done for a single-phase situation. So we're going to just use the ideal transformer for this part and look at how the voltages change based on the configurations. So if you remember, we have two types of configurations, delta and Y, and we're going to look at how these are connected together. So if you had to connect these in delta and Y, how would you connect them? So remember, your delta connection goes like this, and your Y connection like this. And we have the dots here. So we could see that in the delta, well, let's start with the star, since the star is easier to see. In the star connection, all the negatives, which are the terminals without the dots, are tied together. So if I wanted to connect these in star, I could start by doing that, connecting all the negatives together. And then the positives on the outside. So this side of the winding is in star, and I could do that with, for the transformer, I could configure each side independently, not because the one side is a star, the other side has to be a star as well. So I'm going to configure the next side, the secondary side, in a delta. So you'll see the delta here, it goes from dot to no dot, dot to no dot, dot to no dot. So I'm going dot to no dot, dot to no dot, dot to no dot. And I take the windings out of the terminals with the dots. In this case, a terminal with a dot is also a terminal without a dot, so you could take it basically out of any node. There are only three of them. So I'll take it from here, and from here. And then I have this side of the winding is Y, and this side is delta. So that's exactly what I have here. If you look at these configurations, I have here delta and delta. You'll see dot to no dot, dot to no dot, dot to no dot. And this side is also delta, and then I have Y and Y. All the negatives tied together, all the negatives tied together. So let's see if we could track some of the configurations here, track the voltages across these configurations. So we could configure the source here, the transformer, and then the load. So this side would be a star, all the negatives tied together. Then we have to figure out what is this connection here. So take a couple of seconds and see what you think it is. You could pause the video at each point here and see if you could identify what the configurations are for each part, and then we'll go through them. So if you did that, we could see here that this goes from positive to negative, so it should be a delta. And on this side again, positive to negative, so we should have a delta. And then on the load side, all the negatives tied together, so it's a star. Star, delta, delta, star. So now if we want to track how the voltages change across here, this is the important thing. What the transformer transforms is the voltage which is directly across the terminals of the transformer. So in this case, I have a star configuration where the voltage is V. But what comes to the transformer is not the voltage V, but the voltage from line to line. So you can see here, this is one line here, and this is one line here. So it's not the phase voltage, but the line voltage that appears across the transformer, the line-to-line voltage. So the voltage, the magnitude of the voltage across the transformer would actually be √3V. And then on this side, I would get N2 on N1 multiplied by √3V. Now on this side of the transformer, the load is connected in star. So because there is a star load, I know that the voltage across here is not the voltage from line to line, because what I'm connected to here is the neutral point. So what I get here is the phase voltage, and we know the phase voltage is, for a star configuration, is 1 over √3 multiplied by the line-to-line voltage, which is N2 on N1 by √3V. So I get N2 on N1 V. So it just happens to work out to the transformation ratio, the turns ratio of the transformer. But this is the way we have to do it. We have to look at what are the actual connections across the transformer. The typical mistake students make here is that you see V volts here, so you say, well, this is just V N2 on N1 multiplied by V volts. But you have to look at specifically what is across the transformer. So let's do it for another one now. So here we have, let's see firstly if we could track the configurations. So again we have star, we have star. This side we see all the negatives tied together, so we have a star. Then we have positive to negative, positive to negative, positive to negative. So that's a delta. And here we have again positive to negative to positive to negative to positive. So we have a delta. So let's track the voltages here now. We have V volts, and then line to line would be √3V volts, but we want this voltage here. So the line to line voltage is √3 volts, but the voltage across the transformer winding is not the line voltage in this case. It is the line to neutral voltage. So this would be 1 on √3 multiplied by the line to line voltage, which is √3V, which is equal to simply V volts. I come to the secondary of the transformer, and across the secondary of the transformer I get N2 on N1 V. And this is connected in delta. So the phase voltage, remember when you're doing the transformations across the transformer, you always work with the phase voltage. So I have N2 on N1V is the voltage across this phase of the secondary. So if I want to now find the line-to-line voltage for the delta, I know for a delta configuration, the phase and the line are the same. So I have N2 on N1V, and this is delta here, the load. And again, for a delta, the line voltage and the phase voltage are the same. So I have N2 on N1V across the resistor. So this is how we track the voltages across. Let's do one more example. So we have, in this case, positive to negative to positive to negative. We have a delta connected source. Here we see all the neutral points tied together. So it's star connected on this side. Here we have delta connection, positive to negative, positive to negative. And here we have a star connection. So let's see what we get. We have the phase voltage here is V volts. Since this is a delta connection, the phase voltage and the line voltage would be the same. So we have V volts here. Now we have a star connection. So we know the phase voltage for a star is 1 on root 3 by V volts, which is the line voltage on the star. This would give us N2 on N1, 1 on root 3 V volts across here. This is in a delta connection. So for the delta connection, we know that the line voltage is the same as the phase voltage. So we have again here N2 on N1, 1 on root 3 V volts. And now we need to find the voltage across the phase. And this is a star connection. So we know for the star connection that the phase voltage is 1 on root 3 times the line voltage. So we have 1 on root 3 multiplied by 1 on root 3 N2 on N1 V volts, which would be 1 on 3 N2 on N1 V. So sometimes you because of the configurations of the windings, of the transformer windings, you might find you put in V volts here, you have say a 1 to 10 transformation ratio here, but you don't get 10 times the voltage here. You get something else, and that you might get just 1/3 of that. And the reason for that might be the transformer configuration. The delta to Y configurations, because of how the relationship between the delta and star phase and line voltages, you could in effect reduce the voltage or increase the voltage more than the turns ratio that is appearing on the load. So in summary, by now I hope you could draw the connection diagrams for delta and Y connected transformers. Remember, the delta connections go negative to positive, and the Y connected transformers, we tie the neutrals together and we take the terminals out of the dotted terminals. And you should be able to calculate voltages and currents in three-phase transformers. We looked at the voltages only. The currents, same thing. We use the same procedure, except now the relations would be reversed. For the Y configuration, the phase current would be equal to the line current, and for the delta configuration, the line current would be root 3 times the phase current. But the way we do it is the same. And remember, what we do is from the device or from the source to the transformer, we always find the line-to-line voltage as the intermediate, and then we use that line-to-line voltage. So we have some system here and the lines are coming out. Then we have the transformers, the lines are coming out. We always want to find what the line-to-line voltage is, And when we do that, then based on whether we have a delta or a y, we could find what the phase value is here. So we always go from the component to the line to line values and then back to the other component. So that brings us to the end of our section on transformers. The tutorials will be up and you should attempt them and write on the forums and so on. And I will try to put up some questions, exam type questions, worked out so you get a better feel for how the questions are tackled.